from the Department of Statistics, who's a great statistician, but also a great innovator in scholarly publishing. He has an online journal with a new paradigm of peer review, and look, it's called research.one. So I'm strongly recommended. Thank you.
Okay, thanks. All right, it's good to be back, and I'm going to talk. I'll talk about some observations and open problems for the Alphapermanent. And I'll explain what that is in a second if you've never heard of the Alphapermanent before. But what I want to emphasize and what I want to talk about here are a few properties of this function. It's a function of a matrix. Some of these identities, much of this goes back to a paper I wrote a few years ago now, where I made some observations about some algebraic identities. And now just recently, I've made some additional observations, and a lot of this actually comes about from experimental work. So I'll explain a little bit about how some of these identities actually came about unexpectedly.
They are all proven, or are some of them still open?
The ones I'll show are proven, and but the interesting part, at least to me, isn't necessarily the identities, but what they might suggest for some things to do down the line. And so what led to the conjecture was experimental work, but I'll also talk about the limitations of computation when we're working with the Alphapermanent, because it's a computationally difficult thing to work with. So definition. So there's a parameter alpha, which we can take to be a complex number, and a matrix, an n by n matrix. So the Alphapermanent is defined as a function of a matrix as a sum So this is the expression where Sn is the symmetric group, acting on n elements, and I write number sigma is the number of cycles of sigma, permutation sigma. So just to make sure we're understanding what this is saying, let me do a couple examples. Simplest case permanent of a simplest non-trivial case permanent of a 2 by 2 matrix. So we have two permutations. There's two permutations written in cycle notation. There's always the identity permutation, which has two cycles. So we get an alpha squared times the diagonal entries. And the other one is the transposition, which has one cycle, alpha times the off diagonal entries. So some interesting special cases. Alpha equals 1 is just the sum. Alpha equals minus 1 is the difference. And this is just the determinant. And the case alpha equals 1 is usually just called the permanent.
Did you make up the definition, or it existed?
No, this this existed before. I think it's from the 90s or so, but there is some motivation for this, and I'll explain that in a few minutes. Okay, so there's this family it has this parameter alpha, but it includes both the permanent and seems to have something to do with the determinant, but let me write out the 3×3 case just to make sure we don't draw too many conclusions. So in this case, there are 6 permutations. And each one gives us a term in this expression. 3 cycles times the diagonal entries. Now in this case, we'll get the permanent again with alpha equals 1, but the -1 case corresponds to the negative of the determinant. So that's the definition. And just some general facts. As I've already mentioned, the 1 permanent is a special function called the permanent. The alpha permanent is a more general form of the permanent. I should say that both the permanent and the determinant, of course you've heard of the determinant before, these are well-studied objects. The alpha permanent is a little bit more obscure, but there's some reasons to study it to come up in statistics and in probability theory. So this is just called the permanent. And in general, the -1 permanent is -1 to the n of the determinant, times the determinant. Okay. So some motivation. So why am I interested in this, and why are people interested in this in general? So the earliest interest in the permanent in general, and not the alpha permanent, but the earliest interest in the study of the permanent was algebraic, where so going back to actually the early 1800s, they were interested in studying, well, given there's a pretty close, pretty close connection algebraically to the form of the permanent and the determinant. So understanding that relationship between those the algebraic forms, this was something studied by Binet and Cauchy as early as 1812.
Do you know who made up the name dominant?
I don't remember offhand. It may have been Cauchy. But this information is coming from this book on permanence. So this is a book by Mink, 1978, on permanence. And in the back of this book, he has a bibliography that traces all of the papers that, I guess as far as he knows, have ever been written on permanence. And the first one was 1812. Binet wrote one, and Cauchy. But in here, I'm sure, is the information that you're you could ask. Okay. So there's an algebraic interest, and here we're talking about the interest was in the similarity between the permanent and determinant. But nowadays, this comes up in computer science and the study of computational complexity. So the interest of computer scientists, at least some of them, is in they have these complexity classes of different problems that have different computational difficulty. And there's many such classes. 3 that I'm aware of are P. So many of you have probably heard of P and NP. Sharp P is another complexity class that is related to these. So we can think about these in terms of how. So if we have a problem in this class, we can think of how difficult it is to compute and how difficult it is to verify the result. And so the class P is the class of easy problems. Right? This is things that can be computed in polynomial time. So they can be computed easily, and since they can be computed easily, they can also be verified easily. And an example of this is the determinant. So if you compute the determinant, it's easy for you to compute it. By easy, it means that it scales usually polynomial in the size of the matrix. It's easy for you to compute it, so I can check by computing it myself. NP are hard to compute, but easy to verify. Think of it as. So an example of this is the subset sum problem. If I give you a subset or a set of integers or a set of numbers, I ask you whether there's a subset that sums up to 0. So as the size of this set grows, it's hard to find such a set, but if you give me a subset, I can check whether or not the elements add up to 0.
It's believed to be hard.
This one is.
It's believed to be hard. If NP is not equal to 2.
Well, right, okay. Well, there's that, yes. Okay. And then sharp P are those which are believed to be hard to both compute and to verify. And the example in it is that the permanent falls in this class. And this was a result in a paper 1979 by Valiant, where the permanent was where he studied the permanent as and presented it as what's something called sharp P complete, meaning that when you solve problems about computational problems about the permanent, you are saying things about an entire class of problems in this sharp P class. Okay. So on the one hand, we have algebraic similarity, but there's very different computational behavior between these objects. And one of the primary reasons to be, well, from my point of view, to be interested in the permanent was in how it arises in certain statistical problems. So there's some applications in which the permanent comes up, and since they come up in applications, this difficulty involving computation has some relevance because it prevents us from using certain models that are described in terms of the permanent. So some examples of where this comes up, there's a class of stochastic processes called permanential point processes. And these are used to study, so think of a point process as a way of studying the distribution of points in space or particles interacting in some environment. So these point processes are used, among other places in physics, to model the way that particles interact. Where I haven't worked with permanential point processes, but I've worked so where I work mostly with permanence is in the study of models for random set partitions. And these are models that come up in population genetics. Okay, so those are the, so that's the motivation for this, which is that I was initially studying a lot of problems in study of random set partitions, and I came across the permanent somewhat accidentally, but fortunately, and it turns out there's a close connection between a very well-known class of distributions on set partitions and the permanent. And so let me describe that a bit before I get into some of the algebraic and combinatorial features of this object. So let's see, some So the first identity I'm going to talk about is a simple one, so it's identity 0. You could calculate, you could easily figure this one out if you were so inclined. I'm going to write, so I'm going to talk about set partitions, so the collection of all set partitions of n elements. So, for example, for n equals 2, there's 2 partitions. N equals 3. There's 5. And n equals 4, there's 15. There's 52 for 5, and so on. And here I've just organized them in terms of how many blocks they have. So I'll call the equivalence classes, I'll also refer to those as blocks. So there's 2 blocks, 3 blocks. For any partition, I can identify any partition as a matrix. It's an n by n matrix, where I define the ij entry to be 1 if I and j are in the same equivalence class and 0 otherwise. So, for example, this would be the matrix representation of this partition here. And so, once we represent partitions as matrices, we can think about taking the permanent of a partition, or applying this function to a partition. And if we do so, the expression for this, we have a nice simple expression, which is it's a product over the blocks of alpha, and we have a rising factorial, the cardinality of the block. So this is alpha. So over here, the permanent of a block diagonal matrix is the product of the permanents of the blocks. We would have alpha squared plus alpha from here times alpha. So this is just alpha plus 1. Okay. Now I'm going to use that to give you the first substantial identity. So this is everything so far could easily be, you could easily do yourself. For two matrices A and B, I'll define the Hadamard product A dot B. This is just the element-wise product. So for two parameters, so now for two parameters, alpha and beta, I have the following observation. The permanent, that the alpha beta permanent of M, the alpha times beta. So the definition of the permanent as a sum over permutations, I can express this as a sum over partitions. Specifically, I mean set partitions. So talking about set partitions always, not today. I won't talk about partitions of an integer. Beta, following factorial, the number of blocks of pi, alpha permanent of M, Hadamard product with pi, where so beta falling, this is falling factorial, and number of pi is the number of blocks of pi. So when pi is a partition, this means the number of blocks. When it's a permutation, number of cycles, and there's a connection there as well. Okay, so this is the first identity, and it's the first thing I had proven in that earlier paper. And I want to tell a little bit of a story about this, but there's also some questions that I still have lingering about this identity. But the story is about how I came to find this identity, and it was by use of some computational verification, but also a bit of a hunch based on a probability distribution that I was studying at that time called the ewtns distribution. And I've talked about this distribution in the seminar before a couple of years ago. So the ewtns distribution is named after Warren Ewens, who's a statistician and a population geneticist. And this is a probability distribution on partitions, and it assigns probabilities as follows. So there's two parameters. Parameters are alpha and theta, and it assigns probability to partition pi according to this rule. So we have a rising factorial involving the number of blocks. We just have a normalizing constant that involves the size of the partition, and then we have some product over the block sizes. And if you were to look this up, so if you wanted to look this up in Wikipedia or something, actually it would go by the name, I think Ewens distribution, you would get it, or Ewens sampling formula, and also there's something called the Chinese restaurant process, which is a process used in statistics that's closely related to this distribution. Okay. So I was working with this distribution.
The minus signs don't make it negative? Or cancel out?
No, it's a weird way. This is how it's usually written. It's the most compact way to write it. But so this minus alpha is in a rising factorial, so it's going to come out as minus alpha, and then the minus minus.
Okay, so
yeah. So that's, and this is going up. Oh, I should write the parameter space, which is this is we need alpha to be between 0 and 1. In that case, beta has to be bigger than negative alpha. Or if alpha is negative, theta has to be equal to minus a positive. to an integer multiple of alpha. Okay, so that's the region on which this is a proper probability distribution. So I was studying this, and I was looking at this distribution, and I see all these rising factorials, and I note the connection over here, and I was curious whether or not these could be re-expressed, or these were actually just some permanent, in a very special case of a permanent. So this suggests another distribution, going back to the identity that I showed you here. As long as everything here is positive, this part gives you the normalizing constant of a probability distribution. So we have another family with 3 parameters.
So this is a crane distribution.
If you want to call it that, sure, yeah. But I can't do that, so you can start. So why this? So this becomes interesting because it has this extra parameter. It's a little bit more complicated, but just to note the connection here is that if we take alpha to minus alpha, beta to minus theta over alpha, and m to the matrix of all ones, then this gives us the Ewens alpha theta distribution. So a way to interpret the Ewens distribution, and in the study of random partitions and statistics, the Ewens distribution has a property that's called exchangeability. And what that means is that if this is going to assign equal probability to any 2 partitions that are, so if you just think of keeping the structure of the partition, keeping the block sizes the same, but switching around the elements, then they're going to get the same probability in this distribution. So one way to interpret that, especially in light of this, this more general family, is that this matrix M somehow gives us a description. It's a parameter that's describing the way in which different particles interact with one another. And a matrix of all ones is like a homogeneous environment in which they interact. More generally, we might not have that, so we have this family of distributions. Okay. Let's see. Another consequence so one further consequence is that when we realize the connection, the expression of the determinant in terms of the Alphapermanent, we can first there's going to be a -1 here. We can express the Alphapermanent as a linear combination of determinants. But, so we talked about the computational complexity. The determinant's easy, the permanent is hard, and the Alphapermanent is believed to be even harder, or at least as hard, for alpha other than 0 and -1. So we have something easy, something hard, but there's a lot of terms in this sum, so this doesn't seem to help us right off the bat. One possible way that this might help us, and I'll come back to this a little bit later, is that if we take k to be positive integer, then the negative k permanent, I guess I still need this, -1, has this expression, which is the same expression, but since we have a falling factorial here, this is going to get zeroed out for any partitions with more than k blocks. So there are fewer terms in this expression, still a lot. So in general, this is now a sum over, this can be simplified to a sum over partitions having at most k blocks. And this asymptotically is like k to the power n. So there's still a lot of those terms. But given the relationship between the negative one permanent and the determinant, and maybe a slightly simpler expression here, I wonder, so first question I have, and this is admittedly this is an ambiguous question, but is whether or not there is a, is there any interpretation of these minus k permanents as generalized determinants or something like that. So I won't say what I mean by that, but I'm curious. So, for example, the determinant has an expression, has an interpretation in terms of the volume. In terms of volume, I wouldn't expect that these negative k permanents have such a thing, but you know, what is the connection there, if anything? And so that brings us back again to what was originally motivating the study, the study of these objects, the similarity to the determinant. Okay. All right. So a second identity that I won't talk much about because I don't know, it doesn't seem to lead me very far, is the permanent of a product. So you know that the determinant of a product is the product of the determinants. Not the case for the permanent. This is a sum over n tuples of integers 1 through n, and they can repeat. So if they didn't repeat, they would just be permutations. But this is over all possible strings. And it has a little bit of a, the way I write it is a little bit strange. But where Bx, so Bx is a matrix whose ijth entry, whose ith row is the xith row of B. So there can be repeated rows in this, there will be repeated rows in B, but in the case of alpha equals -1, this is the determinant, related to the determinant. So we know that the determinant of a matrix with two identical rows is 0, so this is going to only count terms that in which all of these indices are different, and that's just a permutation. And so we get back the case where the determinant of a product is the product of the determinants. But in general, for alpha not equal to -1, this is not true. Okay, finally, and this is the one that has me, I think, leads to the most interesting observation of today and raises the most questions, of which I don't have the answers, but is certainly worth exploring if you're so inclined. The permanent of a sum written this way. So I have a sum over subsets of n of this expression where so is of ij, this is a diagonal matrix where there's going to be a 1 if I equals j and I is in S and a 0 otherwise. So this is the identity matrix, but I only count the diagonal entries that are in S. So when I multiply it by A, all I get back is just the part of A that's indexed by S. And then I add that to the part of B that's indexed by S complement. I get a whole matrix out of that. Okay. So 2 observations. First, so these two observations, and the reason why I felt inclined to talk in this seminar was these were observations I had originally made just by playing around on the computer, testing out different, computing different things, and seeing that these relationships seem to hold, but then afterwards realizing that actually I should have known this a while ago because they can be seen as consequences of what I'd done before. But they do give some, at least they're a bit suggestive in where they might lead. So the first one is just that for any matrix, the alpha permanent is a sum of n terms where there's some constant, so it's a linear combination of some constants that don't depend on the matrix. Times these minus k permanents, where the form of these coefficients have a bit of a complicated form. I'm not sure if hopefully don't make a typo here. I'm not sure if it can be written in a nicer way, but it does have a formula. That's for arbitrary alpha, but for alpha equals 1, so just the ordinary permanent, these are binomial coefficients. So I'm able to express an arbitrary alpha permanent as a linear combination of only n terms of these minus k permanents, and that's again why I asked whether or not these, or why I might think that these minus k permanents are somehow special. Another thing I should have suggested, or should have mentioned up here, was when I look at these identities, I've tried to use this identity in particular to see whether or not that one, this one. I mentioned in applications we often want to approximate, well, we can't compute this, so we often want to approximate this value. So this looks potentially promising as a way to approximate this, since I have something here that I know that I can compute. And there's certain statistical techniques that might be worthwhile, that might be useful here. And it seemed from my initial investigation that the case where k was an integer, some of the techniques I was trying out worked much better. They were much more accurate than in this case, and it makes sense because there's fewer terms. And so here the idea would be, if I can approximate these, well, then I can approximate these, because I know I have an explicit relationship between them. But still, I haven't come across really a foolproof way to approximate these. All right. Okay. And the last one is coming from this here. If I consider the case, so what I'm going to do is consider the case A to be lambda times the identity, B to be my matrix M, and see what this looks like when I take the alpha permanent of this matrix. Right? So this is like a characteristic polynomial. Right? This is the characteristic polynomial when we're talking about the determinant. Right? So in this expression over here, we have alpha permanent of lambda times the identity times this filtered out identity. So this is just lambda times the diagonal matrix with ones on the diagonal that correspond to S minus M. And so now we have, in this matrix, we have a piece of it that is just lambdas on the diagonal. And so that's just going to come out as a product of the diagonal entries times alpha, because the only permutation that matters there is the identity. So we get alpha lambda to the size of S. And then here we get the alpha permanent of M, and it's the submatrix indexed by S complement, minus M. The permanent of the negative of matrix is just, you pull out the minus 1 to the power of the size. Okay, so, but I'll just keep it written that way. Okay? So we can look at this. Well, if S contains all elements, then we get alpha lambda to the power n, plus, when S leaves out 1, we get alpha lambda to the power n minus 1. And then we only get one element here, so we get the trace. So we have to add up over all of these. So we end up with the alpha times the trace of minus n. And there's terms in between, but then the final term is just when S is empty, we get the permanent of minus m. So if I'm able to factor this, then what do I get? I would get some expression here so that the product of these values is the permanent of the matrix. So these are something like alpha eigenvalues. So now the questions, so this raises a number of questions, right? So the first question might be, well, what's the relationship of this to, how does the set of these things, how does the collection of these things behave as alpha varies? Is it continuous in alpha? I would assume that it is, but that's something I haven't proven. So that might be, if anything would be easy in this realm, maybe that would be a place to start and to start trying to work from there. But then the thing that I'm most curious about, I'd like to write it down. I guess I have room right over here. Would be so these are some immediate questions. One was the behavior. As alpha pairs. Two, is what's the distribution of these values for large random matrices. So here's where I want to show you
So when alpha is -1, you get something classical?
Yes, and that's what I want to just, it's something, it's an old result. It's called Wigner's semicircle law. Where is this?
You push the tab on the side.
Is it turned on? No?
Nope.
No, it is. It is. So I had my computer, but it wasn't working, so I was going to show this in real time, but this, I guess, serves the same purpose. But here I'm just simulating a 2,000 by 2,000 matrix with Gaussian random entries, IID. Well, it's a symmetric matrix, so the off-diagonal entries are equal on both sides. And if you compute the eigenvalues and you plot the distribution, you get this result. It looks like a semicircle. So if I were to do that again, that would be the same pattern that you would see. And so the nice thing about this, and the nice thing about the determinant, is it's easy. So it's easy to simulate and to observe this empirically by computing the eigenvalues and plotting this distribution. Unfortunately, because of the reasons I described, it's not possible to generate a 2,000 by to compute these values here, or at least there's no way. Well, since it's believed to be hard to compute this permanent, there's not going to be, if you believe that, there's not going to be something like row elimination or whatever to somehow figure out these eigenvalues, or these alpha eigenvalues. And so there's no, as I can tell, good experimental way to get a handle on what the distribution of these lambda values are. It's reasonable to conjecture that it would be, that maybe there's a more general family than the semicircle law, where there would be this extra alpha parameter where the distribution somehow varies with alpha. But exactly what that would be, I think, is an open question. I think it would be a very interesting one, but I suspect pretty difficult as well.
So this is for the classical case, alpha -1.
Yeah, this is the determinant. Yeah, this is the lambda.
So can you do anything for small matrices? Is it analogous, or it's too small?
Well, there wouldn't be, so this is an asymptotic result. So you're scaling, up here I'm scaling the entries of the matrix by square root of n. So this is something that has to do with...
So whatever you can do, you cannot do anything close to this.
Right, yeah. I mean, there's some ways, you can compute, at least on my computer, I can maybe compute the permanent exactly up to, maybe up to 20 by 20, but that might be a stretch. There are algorithms for approximating, so it's possible to use some approximation techniques. Maybe you could get a sense, but I haven't tried that out yet. But I'm interested to do that, and so I present it here in case anyone else is interested as well. But thanks a lot.
Thank you.